they cannot improve the chance of getting pregnancy. So the treatment would not change, but the treatments are expensive. So whether not to go with the treatment also important decision for them. There is no point in going for a treatment because it's a waste of money for them, the patients, because even after treatment also they may not be successful. So in that case, better to take a decision that no treatment is needed for them. That's also decision. So that kind of things. This particular article is about that, and now I will share the a simplicity example based on that. So what did we do was, because the data, the infertile data, the whatever things are there, that we divided into, they are not on any treatment. Those women who are not on any treatment, currently not on any treatment, and the women who are on any infertile treatment currently when they come to the clinic. Number one, this is just a categorization. 0 indicates infertile women who are not on any treatment. 1 indicates women who are on any infertile treatment. And 2 means who conceive out of those treatment. The state. So these are all, by the notation itself, you are all very clear now that these are all states. States in the stochastic process. As I mentioned in the beginning, before you build a model, you need to have clarity on the states and the state space. Then the math comes. And 2 is the number of, this thing, 3 is women who deliver a baby out of women in the state 2. Those who are on treatment, those who conceive and deliver baby. 4 states are there. Then the random variable. Let xn be the random variable describing the status of a woman at time n. So same thing one can do also for a COVID. This kind of things, as I mentioned before the break, discussing with the participant. So you all can yourself after the course, please try to go to a nearest hospital where you have an access and ask them and tell them that you want to build a model or you want to do a stochastic framework of the data, and then you can jointly publish with them. Help them to bring some policy based on your own understanding of the model, and then try to submit an article, then peer reviewed. Automatically you get you all will go to the next level of implementation automatically, because when you submit an article, writing itself is a big challenge. That will make you all really understand the methods very well. First build the model, go to the doctor, build the model, write the article, then submit it in a journal, submit it to a journal, then get a feedback from the journal reviewers. So you automatically see that this entire cycle makes you immediate utilization of the course. And usually the other workshop when I conduct, the in-person, when it is in-person, I would have given a project actually to this kind of things. But now because we are having online, this kind of projects you can take it to after the course, take it to that, and then work on the COVID. Because COVID we have a lot of data in India, and then bring some conclusions which may be new, which may be which can give you a localized.
Excuse me, sir. I have a question.
Mm-hmm. Yeah, please.
Sir, actually, I'm getting a problem in data collection from the hospitals. When we go to the hospitals, they are not agree to.
Correct. Yes. Agree means that you have to have a connection. Like you have to go through. If you are a faculty, you have to go through proper channel, and then ask the universities have to take a permission. It's like something is called IRB. You all must have learned. IRB means Institutional Review Board. Institutional Review Board. They decide, like for example, I have to go for a project for this thing is from a primary data. What I have to do is I have to write a proposal, design, submit to the data owner or a clinician or somebody who owns the data. Then we have to go for agreement that I will keep the data confidential, and I won't disclose the data any other person other than the. confidentiality.
Even if I agreed to give it on a letterhead that I will keep these things within me, and I agreed that I will share my synopsis with them. Still, I'm having problem in getting data from the hospitals, and
Correct.
I try to
I,
solve a problem. Yes, yes,
Correct. I agree. I appreciate. This is what happened in many. Even for me also. Even sometimes they don't share the data because they don't need it. So we have to find somebody who is willing to share. We have to go to them, not those who are. We cannot keep on discussing with some doctors who have no interest to, or they already have
yes,
somebody working for them. They have their own reasons. We cannot deny them.
yes, yes, sir.
They
Sir,
may
my
be right
problem
from
is
their perspective.
yes, sir. Sir, what I want is I am trying to apply basically queuing theory in healthcare management system, but
Mhm.
I'm not able to find any publicly available data sets related to queuing theory, particularly in queuing theory or like Markov chains
हाँ हाँ
and there any from where I data related specifically related to Markov chains or queuing theory related.
well, the Markov chain data means the you have to the raw data, you have to collect the raw data from the hospital, and then you have to convert the data. That's what this thing, the year they don't have the data. The four states I showed, 0, 1, 2, 3, the that kind of states are not, hospital doesn't have the data of that form.
Yes, sir.
You have to, we as a modeler have to go to the hospital and they collect the raw data and translate the raw data into the certain form in which we can analyze the data using the model.
Okay. So
So
basically,
that's
what you have done in your deep learning, this paper which you have shown, this
mm,
is a classification problem, right? 0, 1, 2, 3, 4 are you have classified them
correct.
using
This
deep
is a
learning
Markov
techniques.
chain. Exactly, classification.
Okay.
And then the
Yes,
raw data converted, we convert the raw data. These important questions. What you are asking is a good question. And that is one has to struggle because theory is important. Yesterday I mentioned regarding the application part. Theory is very important. One has to be solid in the theory and then apply. Only theory without application or only application without understanding the theory assumptions is not good. So that's the reason this course, particular training, we all designed a theory part. We have to understand because we cannot make any errors in the random variable decision, the function count, functional form, or the random variable assumptions. So that part you have to all have to be clear. Then the hospital management, either we have to go through our departmental chairs or the vice chancellor or somebody in a proper channel, then they approach the hospital or the administration saying that this is for research and it's a win-win for you students or the faculty. This is a kind of a research satisfaction of the research. For them it is a free service, isn't it? You are doing a free service to the hospital by providing them a good analysis of their data so that hospital also can improve the hospital management.
Yes, sir.
That's what we have to convince them that it is also beneficial for them to have a hospital management. And sometimes hospital also pay the consulting fee for the modelers, saying that we want this kind of models to be done and we will pay this a consultation fee. And they are sometimes the professional hospitals, they know the importance of this kind of work. Or the government data, public data, it's free for all. You download, one has to download that kind of data and fit a model and try to realistically assist the clinical community. Yeah, it's a that's these are important things as and when I also grown up, where to India, PhD days or the post PhD in abroad, other places also the same thing. We have to convince them. It is not easy that IRB and all ethics. We have to maintain the good ethics that the data will be kept confidential and it has to be really confidential. Like other things, We cannot ask, suppose I have the data and कहीं मेरा neighborhood hospital में चला गया, data मिल गया, then obviously, they have to make the data anonymous. They should not keep the names, the patient names, other things there, because if the कहीं मिल गया, कहीं बाजार में दिखा गया, कहीं patient का, अरे I came to know that you are not well, I saw from the data. No, we should not ask them. Even in the office colleagues, if I know a colleague is not well, I should not ask the colleague, I came to know you are not well in a coffee room, in a common room. No, that is called confidentiality. किसी को कभी भी कॉमन प्लेस में जाके कभी चार in front of other people, we should not ask them, I came to know that you have some problem in the disease, you are this thing, how you are doing well. You are asking out of concern. I understand. One, we ask out of concern. कैसे हो क्या हो, लेकिन you are in that way, you are actually violating the privacy of the patient. Patient, आपका अभी blood pressure ठीक है? No, we cannot ask that. You are out of concern, we are asking, ठीक है, that's fine, but that concern should not violate the privacy, because sometimes patient may not like to be disclosed. So these all agreement we have to go through. Like I go through all the agreement with the IRB, that's called IRB, Institution Review Board. They take care, and if I violate, there will be punishment. So under that condition, we get the data, and the data anonymized data. That means the data without any names on it or identification numbers, so that tomorrow or next day after the data analyzed, we cannot again match which patient, who is smoker, we don't know, who is having cancer, who is having non-cancer, who has other diseases. No, that should be privacy of the patient. That's called IRB will take care of that. Then the data becomes rich. That means the scientist has a good respect. That means the scientist work, what is what. It's not about just model building. Model building and ethics makes the good science. And good science always gets respect, and all the community colleagues also get respect. Suppose one good scientist, you are done a good work, and tomorrow you recommend your colleague to a hospital, then they will understand the hospital. Yes, particular so and so doctor has professor has come from a university. We helped her with the data, and now she recommended another colleague of her, and they give value to your colleague also automatically, because one person helped them, and she maintained the privacy and confidentiality of the data. He published well, and let us consider her recommendation. That's how it's also a kind of an English chain. Chain, one helps another, and the one gets a good reputation, good ethics. That's how the build relation between the hospitals. In my opinion, this is the most toughest thing. That should happen anywhere. But then we need to help them. We need to help the hospital community, especially COVID has brought a lot of association between the various collaboration between the various disciplines. So I wish you good luck in that. So I'll come back to the question here. We have because this is tutorial, we are supposed to discuss these kind of things anyway. Practicalities. This tutorial about that. Again, we'll resume after this lecture. Again, we'll resume to the maybe during the lecture we can come back to the theory again. So this example, if you see that the data, as you rightly asked, the day one student asked, so this kind of formulation will not be there in the data. It is our choice. We have to make that. And the hospital doctors would not know what is a random number, random variable, random number, the sequence, increasing, decreasing sequence, or Markov chain. No, these are all unnecessary for them. For them, main is to how to treat patients. And आप उनको what kind of probabilities you are providing them. So now X can be a random variable describing the status of a woman. Why it is a random variable? Because it can predict we are unable to before the experiment, before the woman at the time of walking to the clinic hospital, we would not know the outcome of the woman, whether she will conceive or deliver a baby or she will remain as infertile. We don't know. So it's a random variable describing the status of a woman at time n when she entered into a study at n equal to 0. At a future time n, when she entered the study at n equal to 0, initial value. So S is our state space. Our state space is four states. S equal to 0, 1, 2, 3. Now, once a woman is conceived in which state, that is two. Two is the woman who conceived out of those who are on treatment. So once a woman is conceived, then whether she was on treatment or not is not influenced in deciding the event delivering a baby. So this conceived who out of those on treatment, एक बार conceive हो गया, then there is no treatment. In just that's a clinical point again. The treatment is given, and then after that, the infertility treatment is, I think, not given after that. Then the woman deliver baby or may not deliver. Sometimes conceive and miscarriage or abortion, whatever reason, the baby not delivered. So we don't know. But then from 2 to 3, the step 2 to step 3 or state 2 to state 3, it is only after the conception, delivery baby, and then the woman would not go to the previous steps, or whether she was infertile at some time back or she was on treatment, doesn't matter. These are all not influencing the baby delivery. Whether she was on treatment or not influencing the deciding event of the delivery of a baby. Event of delivering a baby. Hence, the random variable xn follows a Markov chain. So if x5, that means cycles, for example, x1, x2, xn, the timing of the status of women at various intervals, because she was on a treatment, she come to the clinic, the treatment is taken at various time points, and says I started x0 equal to 0. Initially, the woman is in the state 0. Then x1, still 0, infertile. x2, state 1. x3, state 2, that means she conceived. That means she's not on treatment, not suddenly on treatment, and x3 conceived, x4 still conceived, x5 delivery baby, 3. So this probability of x5 equal to 3 given x4 equal to 2. Because the previous states are not influencing the delivery of a baby, because how long she was infertile, or how long she is on treatment is not influencing the delivery of a baby. Because once that woman is pregnant, automatically the previous steps are the joint distribution of this is not needed. So this follows a Markov probability. So suppose we go to the data and we compute a joint distribution of that. That means we are not understand the data properly, and this actually we compute a joint distribution and then we cut a conditional probability. We won't able to get a good correct probability of delivering a baby, because these are all unnecessarily add some noise or add some error to the data, error to the computation of probability. So we just simply compute the probability by taking the conditional probability x5 equal to 3 given x4 equal to 2. Similarly, in general, instead of 1, 2, 3, 4, 5, we can write it as x0, x1, x2, xn equal to 2, xn plus 1 equal to 3, the various steps, then xn plus 1 equal to 3 given xn equal to 2. In general, this is generalized statement. The same thing in generalized statement. Okay, that's how we compute various probabilities. Now only for 2 to 3, that's our end game, because an infertile woman comes to clinic only for delivering of a baby. So that's the main probability. And if you read that article there, you'll see that various other probabilities, computation of various things, all other things are discussed there. But in some, this is the crux of the question is that, can we compute so if this probability is very high for a particular woman, then particular treatment options are given. What type of treatment to be given? So this computational probability is done. When the women come to the clinic, we have to have this kind of probability so that based on the woman's characteristics, genetics and other things, age and gender, age and the location, geographical location, not gender, geographical location, all these things, then the probability will change. So the woman walks to the clinic, we can predict the probability of delivering a baby, and then so that she can make a decision whether to go for a treatment, or if it is treatment, what kind of treatment or not. So this will practically help the clinicians, so that their reputation also increase in terms of patient, because patient goes to the clinic only when the patient trusts the doctor, or patient have a good faith on the doctor. So this kind of things, doctor also gets benefited by the modeler or a statistician or mathematician, whoever. So that way we practically try to help to get them benefited, and ultimately patient benefits, but doctor also benefits, because doctor benefits when the patient comes to them. So this is how we can also discuss again when we touch base. We read the article, or during the again you can raise these kind of questions. What someone asked the question right now. Now we'll go to another important aspect. Chapman-Kolmogorov equations. Again, these are all important. These are also important. We'll apply Chapman-Kolmogorov also in various other places of the real world. That's why, what is the theory behind Chapman-Kolmogorov? Let us understand. So for a discrete time Markov chain, already that name is suggests is a Markov chain property. Just now we saw discrete time. That means you are measuring, or you are calculating the value of random variable, or you are measuring the random variable, or observing the random variable, whatever way you want to word it, discrete time with some state space. Pijmn already notation you saw. That means state I, m stands for time step. Please concentrate on the notation here. We just discussed in the previous slides there. I stands for the state, the suffix this state, this is time. So state I, random variable, was at state I at time m, and the random variable reached state j at time n. Now on the right hand side, I will explain that the summation. I will come to the summation. Now you see that I to j from m to n occurred. The transition of I to j occurred in m to n steps, from time m to time n. So there are n minus m steps, time steps are there to reach I to m, I to j. So this could happen from I to k and k to j. Okay, I to k, k to j. I to k could happen in m to l steps, time step m to time step l, and k to j, that means at state I xm is equal to I, isn't it? The notation what you just learned, x suffix m means random variable at time m reached state I, and random variable xl equal to k. This means here wait a minute, instead of messing up, let me write a fresh, let me introduce a fresh slide here. Wait a minute, I'll come to the summation later. Just meaning, okay? So Pij, P, you can add capital, as I wrote a capital there, but let me P I to k m comma l multiple and and means multiplication, and pk to n, k to j in from L comma n. So what is the meaning of the in terms this? Let us expand this. This means this is equal to probability of this m. M happened first, then L. So this x of m equal to the first suffix I. So as I write, if you have a pen and paper with you, please write yourself just to make sure. Xm equal to I, given that, and then reached XL. This is a time step. L is a time step. So XL equal to J. Sorry, here K. XL equal to K. Probability of that. That means a random variable. This means here I to K from M to L. And then it's that means n means when two events occur A and B, we multiply, and A or B we add. A and B in previously counting process we added because this event or that event. That means we are adding those probabilities. Now here this event and that event, because I to K and K to J, and because ultimately the random variable have to reach J. So probability X here given part. So it started from, it reached I to K. So again it has start from K. What is the K time? XL equal to K. And it reached what? K to J. So J at what time? N. Xn equal to J. Now on the left hand side you see that Pij Mn means probability that what is given X started from Xm equal to I. I started from I. Suffix is a state. Here is a time. And then reached Xn equal to J. So probability of occurring this J. Now you see that your common sense says that K is what? Arbitrary. K is arbitrarily pick some state between I and J. K is a state between I and J, some state. I, J, K, some others say I1, I2, various states are there. So I to J through K. So, sorry, instead of K, I should not, don't want to use I1. So what I will do, I1, I2, I3, I4, and so on. So K is arbitrary, and so on. Many states are there. So I to J could occur from I to I3, isn't it? I to I3, and then J, or I to I1 to J, or I to I1, I1 to I2, I2 to J. Isn't it? These all probabilities are there.
But sir,
So K is, yes, please.
yes, sorry to interrupt you, sir, but don't you think that this calculation is computationally so very inefficient, considering the huge size of the state space, unless we compute this entire thing probably in the bottom-up manner?
No, it is not because this is exact.
This
This is
is
not
exact, sir, but then you see, even if the value of k is, say, there comprises of, say, only 6 elements in the state space, say 100 elements in the state space, say, so we'll have to explore a large number of the possibilities to get this value ij and then mn in the left hand side.
Yeah, computers can do. Computers don't make a mistake even though it's large and millions of data also computer can compute.
The possibility would be huge, sir. I think. How do people usually compute this value in the right hand side?
You
Using
mean
some software
the
packages or what?
no? That's what I'll explain you.
Okay.
That's a computational thing. We'll come to that computational complexity.
Yes.
Computational
Yes.
complexity. We are not discussing. We are discussing now theory. I will come to that
Okay. All right, sir. All right. Yeah.
because, but we do in one line. We are computer would not make any mistake if the theory is correct.
Right. That is there.
So we are discussing the exact theory here, exactly what is happening because just for the sake of computational simplicity, we cannot make a oversimplification.
Right. Right.
Too much simplification doesn't mean that that is correct or unnecessary
Uh,
complication also. Yeah. So we'll
right,
come to
sir.
that. Let me understand the meaning of K here.
Right, sir. Right, sir.
So this is important. Why do we use Chapman-Kolmogorov is the central of the stochastic process. So the second day itself, you all reached this position, this level. I should all appreciate you. Chapman-Kolmogorov, very very important. Conceptually, classic result of a stochastic process. Entire course. Of course, there are other classics also there we'll touch. But Chapman-Kolmogorov equations is one of the classical results of the stochastic process. So let us understand this thoroughly. No compromise on the. So the what is happening here? Suppose there are so many states are there. I to j can reach either directly, or through some other state. Similarly, if it reaches through others I to some other state, and then some other state to j has to come back. That's because we are computing the probability of reaching j from I from mth step to nth time step. So I to k to a j means k is an arbitrary here. K arbitrary means k could be any of these. Any of these. It need not be just directly. K could come from I to j or I to I3, I3 to j, or k could come from I to I1, I1 to j. Your k could be I1 or your k could be I3, your k could be I4, your k could be I2, whatever. So in between it can come from, so all such case, so it or, so you see that probabilistically here we are applying or I to I3 to j, or the transition could occur from I to I1 or to j, or I to I4 to j, so on. So that or everything is or all the options are there. So k is an arbitrary. That's why we are summing up here over all such case. K belongs to S. S is a state space. So that's why Pij Mn equal to sum of k belongs to S. All such case that jump from I to k to j. See that here. I to k in how many steps? L minus m steps. L minus m time steps. Or I to j and k to j in L minus n, n minus L, n minus L time steps. So this is what the idea of the Chapman-Kolmogorov. Oops. Yeah. This is that is what the Chapman-Kolmogorov says. Summing over all the k belongs to S, where m is m less than L less than n means the time step L lies between m and n, strictly less than. So that's what we just saw in this thing I just drawn. So the small result, um, before you see that, we all know that once you understand this particular relation, that means the states, suppose we divide a space S equal to E1 union En, which are mutually exclusive. Suppose A and B, you take a mutual exclusive. That means here, let me, in the previous slide itself, let me draw here. So you take a space and you divide that into two pieces, A, B, two events. And occurrence of A is mutually, A and B are mutually exclusive. So your space A equal S equal to, this is your S equal to A union B. A and B are mutually exclusive. Or you can have a space A, B, C. A, this is A, this is B, this is C. Your space S. So S equal to A union B union C. Whatever way. So now, so we write E1, E2, that means A1, they are union of N sets, the mutual exclusive. Then if you write a set A subset of S, for some set which is subset of this, you take a subset, this one, you take a subset of that A, then probability of A is equal to probability of A intersection EI. If you take a set A such that subset of S, that means set A. Now this A in the previous here, that idea is you take a set which is, in this set A, if you take this space A intersection, this piece, small piece, this piece has elements from A, this piece has elements from B, the circular piece. Now if you take another circle or some shape, arbitrary shape, that has a ABC. That's what it means. So that result anyway, that comes from the probability. If A, that means probability of A1 intersection A2 is sum of probability of A1 intersection A2 intersection of AI. So intersection. So probability of the circle, if you want to compute, that means probability of A intersection this piece, that is only this piece, this lines. Again B intersection the circle. Again that means B is entire B. This part is B intersection. This is this piece. So probability of A intersection B is nothing but A intersection B can be written as probability of A intersection B intersection this piece. So this circular piece, that's what it is. A1 intersection A2 intersection EI. So EI generalized, more generalized, you think on that again. So this, suppose you take A1, A equal to a intersection of these two, new set, you can write a A1 intersection A2. Now conditional probability, A1 intersection A2 is nothing but, in any two sets if you take, probability of A1 intersection A2 is nothing but probability of A1 intersection A2. A1, any two sets A1 given A2 multiply probability of A2. So using that, you see that in the previous slide, A1 intersection A2, because we already wrote that A1 intersection A2 is probability of A1 intersection A2 by probability of A2. Because you see that previously, here, this is probability of A1 intersection A2 equal to probability of A1 given A2. So probability of A1 intersection A2 equal to probability of A1 given A2 multiplied by probability of A2. So probability of A1 intersection A2, A1 given A2 would be, this would be equal to this divided by that. Probability of A1 intersection A2 by probability of A2, condition probability. So using that result, so you see that probability of A1 given in A2, you bring that into this slide. So A1 given A2 by probability of A2. So this by A2, probability of A2. This is by probability of A2, A1. And now expand it, you multiply here this equation, you multiply by probability, just algebraic manipulation, A2 given intersection EI. So probability of A2 intersection EI, multiply and divide by same. Now you see that probability of A1 intersection A2 intersection EI is, again, if you consider these two pieces together, these two sets together, that means A1 intersection of this piece by, that means this intersection, that means this given that multiply by that. So probability of different color. Okay, let me change the color. Probability of A1 intersection A2 intersection EI. So if you consider these two together, that means this is the probability of A1 given A2 intersection EI multiply by probability of A2, this is probability A2 given intersection EI. Sorry, what happened?
Professor Rao,
Ah,
I'm audible?
yes, sir.
Okay, we can continue this in the next tutorials.
Yes, वही मैं सोच रहा था, actually late हो गया. Yes,
Okay,
we'll
it's
continue that
already
in next.
9:34 in the
हाँ,
Indian
तो मैं
time.
क्या करूँगा? What I'll do is I have so
You
next
can
two
share
slides.
slides.
Yeah, up to the end of the proof मैं आज ही भेज दूंगा उनको, so that they can come prepared, see the lecture, see the slides.
Sure, sure.
Is that okay?
Is it right?
I have two more slides are there for today's lecture. Two slides including the